We are happy to have today Matt Walter. So Matt is faculty at TTIC for almost a decade now, I think, and working on all aspects of robotics and interaction. Usually tells us about underwater stuff. I don't know if
no underwater.
No underwater today. Okay, so today is going to be an overwater talk. Okay.
Breathe.
Thanks.
Okay. Thanks. Okay, so I'm going to tell you about work that I didn't do, but a lot of other people with me did. So a bunch of folks at TTI, U Chicago. Some were at TTI U Chicago, now have moved on. So Takuma is now at DeepMind, and then Kevin is now at MathWorks, but hopefully we can convince him to come back here for his PhD next year. So we're going to talk, this talk, as the title said, is about robots that learn via imitation and reinforcement learning. So this idea of spanning the spectrum from pure imitation learning to reinforcement learning and really someplace in between where we're combining both imitation and RL. And the goal here is to get robots that are really more competent than what we have today. So how many people have a robot in their home? Is it? Really? A Roomba? How many people have a Roomba? So Roomba is a robot. It's maybe arguably the most useful robot that people have in their homes, probably the only robot that most people have in their homes. And it's useful. It's not terribly intelligent, but it gets the job done. So there are plenty of videos of people putting their pets on Roombas. Roombas are not very intelligent. They've gotten better. Before, it used to basically just do a random walk. Now Roombas are supposedly building maps and using SLAM to more efficiently clean the floor or chase ducks. But really what we want is a general purpose household robot that can do more useful things beyond just cleaning up a mess. So this is a video that was released just maybe a week ago, 2 weeks ago by Physical Intelligence. Sergey Levin and Chelsea Finn, a spin-off. And they've trained this robot actually via, I guess they're not explicit about it, but presumably some form of imitation learning, and we'll talk a little bit about that. So this robot is clearly performing useful tasks. Right? Actually, I don't mind doing laundry, but I guess most people probably don't like doing laundry. So now, in principle, this robot can take out your laundry and fold it, albeit a little bit slow. But it's pretty competent. And this, you can watch the whole video. It's making coffee. What's that? Yeah. So it's not the most. Yeah, exactly. It's not the most efficient, certainly. And who knows how general it is, right? So if the table surface looked a little bit different, would it be able to do it?
Like, is this a product or?
It's not. I don't know. No, it's not a product. It's a startup. I think just.
So this
demo to raise
this
money.
Is like a kind of demo. Like for all we know, there's a remote controlled.
I would hope not. I think it's said autonomous, so I think it's not. But I don't know how generalizable their policy is. Okay, so how would we want a robot to do our laundry? How might we tell it what to do? Okay, well, the way that we used to do things is just open loop control. So we take our robot, or whatever if you want to call this a robot, and we define some sequence of actions. And we'll do this manually. This should play this video, how the sausage is made. This video, so we'll come up with this stream of actions that perform some task. And again, typically this is done by hand. And we'll tell maybe you could argue this is not a robot, but let's call this a robot. We tell the robot to repeat this sequence over and over again. And that's what robots are good at in these highly controlled environments where the task is highly repeatable. This is, a valid policy, right? A valid strategy, just open loop control. And you can make it a little bit more sophisticated. You can have the policy be a sequence of actions that varies depending on the initial state. That's nice because it's easy to design, it's easy to understand.
I'm just so I'll ask you the question that you probably wanted to ask. I mean, why is that? You described that as a robot. Is that a robot based on your definition? Okay. Is my laundry machine a robot?
I would probably say no, actually. It's arguable what is a robot, but I say a robot is something that senses, plans, and acts. And that robot isn't doing any planning. It's just spewing out a sequence of pre-recorded actions. So I would say that's actually not a robot. But you can imagine...
Oh, so the washing machine is a robot?
Yeah, it's fuzzy. I guess it does do some sensing, but Okay, so open loop control has some benefits, but it's not robust. That sausage moved to a different location, it's going to fail because it's going to execute the same action it did if the sausage had been where it thought it was going to be. So what we can do next is we'll close the loop. So we'll add some observation. So the agent here is interacting with this environment. We're going to picture it as a world. It gets its state ST. This might be low-level symbolic state, or it might be an image or some other observation of the state. And what the robot is going to do is it's going to have some policy that's going to determine what action to execute based upon the current state, not just the initial state, as I've mentioned before. You can sort of think of humans as doing this. Okay, well, we go back to our factory, and now we have a factory that's not just making sausage or slicing sausage, but maybe making cookies, doing something a little bit more sophisticated. So here there's going to be some randomness. The cookies' shape is different. They're not always appearing in the same exact location. So we need some notion of state. You can imagine here it's where the cookies are. And then we have some closed loop controller that's picking these cookies up, or whatever these things are, biscuits, and then placing them in some container. So a little bit more sophisticated, right? So how might we do this closed loop control? And again, I'll skip over this, but you've taken a controls class. The classic way of doing this is with PID control. Another approach is to do optimal control. So you have some optimization, you have some function you're trying to optimize, whether it's minimizing a cost or maximizing, let's say, a reward. Another, and what we'll focus on these settings, is reinforcement learning. And they differ. Optimal control assumes that they know how the system behaves. If you execute some action in a state, in optimal control, we're assuming we know the transition dynamics. We know how the world evolves. With reinforcement learning, we don't know that. We don't know what our objective is, and we don't know how actions are going to affect the state. So if the robot does something in the environment, it doesn't know a priori how the state is going to change. Okay. So this strategy in optimal control has been quite effective. I'm sure everyone here has heard of Boston Dynamics and seen Boston Dynamics videos. They're pretty impressive. So one that came out on right before Halloween is their new robot Atlas. So it's this electrically actuated robot, and it's performing what you could argue are useful tasks you might want to perform in a real life environment. So I don't know what it's taking out, these trays, and it's going to walk over and it's going to file this away and put this on a shelf. So again, objects are going to be different. You'll see in a little bit. And again, it's a Halloween video. That's why it's dressed up like a hot dog. But the person's going to come in. They're going to move the shelf. I don't know what they're dressed up as, a pickle maybe. I don't know. They're going to move it, and then the robot's going to be able to recognize that. It's clearly not doing anything open loop. It clearly has a closed loop policy. Boston Dynamics doesn't disclose how their controllers operate, but historically it's been some form of optimal control.
Did Ed tell you?
No. No. Yeah, so you ruined it. Okay, well I guess it's good. So if you saw this person in the background, Andrea, so many of you may remember Andrea Daniele was a student in the lab. He's now at Boston Dynamics. He's been there, I guess, for the past maybe month or so.
Why is he not wearing a costume?
It's a good question. I don't think it's supposed to be in the video. So how are we going to do this? We're going to formulate this in the context of reinforcement learning, and more generally we'll formulate it in the context of what's known as a Markov decision process. So in an MDP, you have two entities. One is the agent. You can think of this as the learning agent. Maybe it's the robot or it's the algorithm running on the robot. And what this algorithm is doing, this agent is doing, is it's taking in the current state, and then it's going to output some action condition on that state. And the function with which it does that is referred to as the policy. So the policy determines the mapping from states to actions. That's the agent. So the agent executes this action. The world evolves. And then the environment of the world provides the agent with its next state. So if you can imagine with the robot, if it's the walking robot, the action might be typically it's joint torque. So maybe you can think if I put my foot here, the environment's going to tell me at the next state what the pose of the robot is, depending on, say, what the surface, what the terrain looks like. And then we're going to assume that the environment is going to give us some reward, some signal that indicates the performance or the suitability of this behavior, of this action. Did the agent do something good? Okay, we'll give it a positive reward. Did it do something bad? We'll give it a negative reward.
Do you think of the embodied state of the agent as part of the environment?
Yeah, it depends. I went back and forth. Sometimes you see the robot put up there, but yeah, you can. It depends. It depends on where you do that abstraction. Okay. And so with Markov MVPs, the fundamental assumption is what's known as this reward hypothesis. That all tasks we want the robot to do, all goals, can be formulated in the context of maximizing some expected future reward. We say expected because we're going to assume, given the Markov and MVPs, that the state evolves stochastically. So we're going to do this in expectation. So what might this look like? Let's go to a driving domain, and I think I used a version of this in the past. You may have seen this GPT-generated video. But let's say we want to learn a policy that lets a self-driving car drive. So the state, again, in this case, is really going to be partially observed, so that's a POMDP, but let's not worry about that. The state is an image, let's say, from one or many cameras on the robot, its velocity, et cetera. Maybe its latitude, longitude. Its actions, right, is fairly obvious. Steering, gas, brake. There are some transition dynamics, as I was mentioning before. T, I think I'll call this P later. But basically, this is a mapping from state and actions to a distribution over the subsequent state. Again, that's the stochasticity of the environment. And there's, again, the reward. And with RL, we're going to assume that the robot does not, or the agent, does not know the transition dynamics T and does not know the reward. If it did, you could solve for the optimal policy by using dynamic programming. But we're going to assume that we do not know either the reward or the transition. So this may be a little bit more formal. So we have, again, this parameterization, state, action, space, transition, reward, a discount factor, but it's not terribly important now. And the goal of RL is to learn, again, this policy, we call it my star, that maximizes the expected discounted reward. So that's what we have. An expectation, R, capital R, again, I might have used this later on, is the reward that the agent gets when it's in state ST, takes some action, ends up in some state ST plus 1, and then we're going to sum that out over the episode over horizon. Yeah?
What's capital T?
Capital T, capital T is the transition function. So basically it's the probability of,
Probability of.
just like, probability of ST plus 1 given ST and AT. Okay, so yeah, if they're known, we can just use dynamic programming, but they're not going to be known. So, why rewards? Why not, what's the benefit of rewards? Well, it's oftentimes, in many of these domains, it's difficult for me to write a closed form expression that defines the desired behavior. I can watch people drive, right? A bunch of people drive, and it's not clear to me what the right objective function is that I would want a driver to optimize. But I can look at different drivers and I can tell generally if one is better than the other. Okay, well, what are things that I want the robot not to do or the car not to do? I don't want it to collide with anyone. I want it to obey traffic laws. It shouldn't speed, or maybe not, shouldn't go too fast, but shouldn't go too slow. So I have these various desiderata, and I can use them to reward good behavior and penalize poor behavior. Okay. So that's this, that's in a nutshell why we might use rewards, and this has been done in a number of applications. Where on the right here is this cheetah robot out of Sung-Jae Kim's lab at MIT. So again, you can think of legged locomotion. It's not necessarily clear what the right policy is for a legged robot to walk. So we'll do reward. But learning from rewards is challenging. So let's consider another legged robot that's arguably much simpler to locomote. One, because it's a simulation, but two, because the action space is much smaller, and that's this ant. It's from OpenAI's GIM, or DeepMind control suite. So we have this ant-like robot, more like a spider, but with 4 legs. And the action space is 8-dimensional. So each leg has 2 joints, and so you're controlling the torques, or maybe the joint angles for these legs. And we have this pretty simple task. Our ant robot starts, we have this maze-like environment, and they're going to be randomly, the layout is going to be random, but the ant starts in one location in the lower right, and the goal is to get it to the upper right. So that's the task. Just get to the elevator lobby, just get to this goal. And the way that we're going to do that is we're going to use reinforcement learning. So we need to define some reward. So, okay, what's the simplest reward you can think of? Yeah, right, +1 when you get, or +10, whatever you want to pick when you get to the elevator log or the goal, right? That's really easy to specify. Now the challenge is a reward like that is a really difficult learning signal. Because what the robot is going to be doing, initially its policy is going to be doing things random. You initialize this, again, policy is basically, or it is initialized randomly, and it's going to basically do, in some sense, a random walk in joint torque space, whatever the action space is. And it's going to stumble around. And it's only going to get a point if it manages to stumble around in the right way to get to that goal region, and that's very unlikely. So if we look at, let's take soft actor critic as one of the standard approaches to RL with sparse reward. And what we're looking at here is the distribution of, this is basically the state visitation count. So the distribution over states that the agent visited with its policy during learning. So as the policy is getting better, you can see here that most of the time, not surprisingly, is spent around here stumbling about. The ant is a fairly stable robot, so it's not too hard. Other robots who would, in the suite would just fall over. It's hard to get up. This one is pretty easy to stay stable, really, but not as easy to coordinate the leg motion to move. But over time, I don't remember how many samples this is. You end up exploring a bit, but you can see that again, it doesn't look like the agent at all got to the goal.
This is really just with the sparse reward of getting there. I'm surprised it managed moving at all. Like, why should it move and not just like sit on its back and wiggle its legs in the air?
With enough random walk, that's what you'll get.
I mean, that requires a whole lot of luck to even take 2 steps. I mean,
yeah, but depending on the horizon.
what horizon? I thought the horizon is getting all the way to the end.
Yeah, well, I think it will terminate after some finite amount of time. So in practice,
I guess I find it hard to believe that it got more than like 2 steps away without any reward.
The ant is not that hard to, if you think of a human, because the ant is inherently stable, so it's not going to fall over, or it's difficult to fall over. So it's not terribly hard to locomote. They just execute a random walk.
But even with a random walk, it would not get so far away.
Yeah, I don't have the videos. It can do, but anyway, it's not clearly not getting any signal to learn. So the next thing that we're going to do, we could say is, well, let's densify the rewards, and that's really the standard practice. Is let's provide as dense of a feedback signal to the agent as we can, so it can learn something useful. And that's again not always easy. Going back to the driving example, it's again I know what a good behavior is, but it's not clear to me what exhibits the right behavior. We've done this for legged robots, ant and other robots, where you want to learn a walking policy. We say, okay, well, if you want to be moving as, let's say forward velocity, that's a denser signal. But, that might, maybe you've seen some of these videos, I don't know if I have it here, these humanoids walking and they're flapping their arms like this. I mean, it is doing the task. Then you say, okay, well, I don't like this behavior. Let me go tweak the reward a little more to penalize this undesired behavior. It's difficult. So, in general, RL is very sample inefficient, particularly when the dimensionality of the state is high and or we have sparse reward. So what can we do? Well, again, that video that I showed at the beginning from physical intelligence, again, I believe it's some form of imitation learning, and that's one way we can make this task more tractable. And again, the idea is that for driving, it's difficult for me to define the reward, but it's not difficult for me to show demonstrations of the desired behavior. So it's much easier for me to drive than it is to come up with an objective function for driving. So that's what we're going to do. So we're going to collect demonstrations, and right now we're going to be assuming that they are experts. So we have, I don't know who the best person in F1 is now, like Michael Schumacher driving around. We're going to collect these trajectories. And the goal now is to learn a policy that is as similar to the expert as possible. Our model, maybe it's a neural network. It's going to output some drives. So this is top-down view of some race course. We're going to compare the way that policy drove to the way the expert drove, and we're going to define some loss. And really what you can imagine we're doing is viewing this as a supervised learning problem. So policy is mapping states to actions. Well, we have our demonstrations. We have a state. We have the action that the expert took. Well, if the robot was or the agent was in the same state, would it pick the same action or not? And again, we can penalize it based upon the difference. Right? And there are various objectives or losses that we can use in this case. treat it as a classification problem, a regression. In the past I've talked about formulating this, and this is really his behavioral cloning loss is KL divergence. Now, there are a number of challenges to this approach. Generalization is one, as I mentioned earlier on, but one is the fact that we're assuming that, is that playing? Come on, there we go, is that the expert is optimal or near optimal. I had to crop out the part where he's showing his underwear. So Mr. Bean, if you've not seen Mr. Bean. Clearly this is not optimal behavior, and you don't want the agent to emulate this. You can think, this is silly, obviously, but you imagine, you look at what Tesla is doing. Presumably, Tesla is crowdsourcing demonstrations of driving behavior from whoever has a Tesla. Again, I don't know what granular or what frequency, but clearly not everyone drives the same, right? So hopefully they're not. Actually, there are stories of people doing something like this in their Tesla, but again, you're going to see behavior that's not optimal. Okay, so what do we do? Well, if you think of the Tesla example, Tesla has access to, I don't know, millions of different drivers. There's not one expert, and they're not even an expert. It has access to millions of, we're going to call them oracles, because that's the term people use. I don't like the term because it sort of suggests to me optimality. We'll call them oracles. Let's say we have our 3 oracles at TTI, right? So we have David, Greg, and Julia, right? So there are the oracles that we can query for examples. How should I drive in this behavior? Look, we care about driving in 3 types of regimes. A rural regime, highway, and an urban environment. Okay, so David is, when I interviewed here, David drove me to the dinner after the first night. He's a very good, a little aggressive urban driver. We got to. So we got, it was in, north of the Lincoln Park somewhere, and we got there very quickly. So he's an excellent driver. David's okay in the highway now. He moved to Hyde Park, and so he's not driving on the highway as much, maybe. So he's just okay. Maybe rural. You don't want to be in the car with David. Okay, but you go to Greg. Greg? Greg is an excellent rural driver. I'm just making these up, obviously. When he's on the highway, though, in the past, he's gotten pulled over by police. So maybe, and then, urban, he's just okay. Anyway, so you get the idea. Julia has commutes every day. She commutes, when she comes to TTIC, so she's really good at driving on highways, but maybe cities not so much. So what you'd like to be able to do is you'd like to be able to identify in which, if I'm in an urban setting, I want to ask David what I should do. If I'm in a rural setting, I'm going to go to Greg. If I'm on highways, I'm going to ask Julia, right? So that's what we'd like to be able to do, right? Yeah, we'd like to be able to learn from these different experts. So that's going to be the focus of that. The first piece is, well, let's suppose I have access to a set of, again, we're going to call them oracles, but critically, we're going to call them black box oracles, meaning that we don't know a priori how good they are. I have 3 people that I can, sort of phone a friend. I can say, hey, Greg, how should I drive in this area? But I don't know a priori if Greg's the right person to ask, or if it should be David or it should be Julia. How do we do this in a sample-efficient way? Okay. So the standard approach, we can do this with behavioral cloning. Behavioral cloning typically, again, assumes that we have access to expert data. But let's assume we did standard behavioral cloning or imitation learning. This formulating as a supervised learning problem, where we want to minimize the KL divergence between, let's say, we could look at the distribution over demonstrated behavior, and that's this bimodal distribution here, pi sub star. And actually, here we're calling it a star, indicates that it's an expert. So that's what we have. So pi star is we had 2 drivers, Greg and David, and this is reflecting their different driving behavior. So if we KL divergence, it minimizes the M projection. So if you take the graphical models class, we talk about this KL divergence. That ends up fitting, averaging. It ends up averaging out the modes. So you're going to get this sort of best of both worlds. I should say best of both worlds. It tries to find some sweet spot in the middle. But that's not what you would want, right? So let's say, if it's either going to the left of the cone or the right of the cone, well, you don't want to pick the middle. Right? You're better off, say, with an eye projection, wherever. You want to pick one of them. Okay, so is there a better approach? Okay, well, one, a naive thing, you could think of the next best thing, or maybe even better, really, that you could do is what we call single best oracle policy. So what we're going to do is we're going to take all our oracles. We have capital K oracles. Your D naught is the distribution over the initial states. But what I'm going to do is I'm just going to pick one. My three drivers, I'm going to say, well, based on my initial state, we have, again, importantly, this V is the value function. So the value function is that expected reward. So V superscript pi tells me the expected discounted reward of following Greg's policy, the expected discounted reward of following David's policy, or the expected discounted reward of following Julia's policy. And what I'm going to do is I'm going to say, okay, I'm going to pick Julia. And that's what I'm going to do. I'm just going to imitate Julia. And that's going to work well in, the highway driving, maybe not so well in the urban driving. So that's one version, one thing that we can do. Maybe we can be a little bit smarter. What if we do this not just at the beginning, but at each point in time, at each state, I say, well, I could see, well, I'm going to look at Greg's value function. I'm going to look at David's value function. I'm going to look at Julia's value function. I'm going to see which one is the highest in that state. And then I'm going to follow that policy for that state. Right? Then the age of the car will move. Then I'll say, okay, well, now I'm going to look at, well, in this state, who's better? Okay, that's reasonable, right? That might yield good behavior. And there's a caveat here that we're assuming we know V, which we don't know. But is there a better strategy? So it's a little bit subtle. Oh, yeah, there. Is there a better strategy? And yes, because basically what this max following policy is doing is it's being greedy. But it might be that instead of following Julia at this state, Greg's value function at this state is maybe lower. But if I follow Greg now, maybe that brings me to a state where Julia's policy is better. Okay, I look sort of one step ahead and see that, well, maybe I should do something that has a lower value function now because it's going to bring me to a state in which I can do better. And so to do this, we're going to be looking at the Q function and the advantage function. Again, I think for time I'll skip through this because again I tend to be long-winded. But it's great. So what the Q function is doing, it's like the value function. The value function is a state value function. It tells us if I follow Greg's policy from this state, what's the expected reward I'm going to get? Say whatever the horizon is, maybe an infinite horizon. The Q function is a little bit different. It says, what if in this state, instead of following Greg's policy, I take a different action now for just one step. So I'm in state S. I might drive it, different from what Greg suggested. That's the A here. That's the A. But then what I'm going to do is after that, I'm just going to follow what the policy said. So let's me see, is there a better action now, under the assumption that later on I'll follow what Greg would tell me to do, but right now could I maybe do better in this one step? And so the way that that's measured is what's referred to as the advantage function. And so in practice, we're leaving this generic f function, but in practice, f is going to be this value function. And what the advantage is saying that, well, if I'm in some state S and I take action A, what f is going to tell me is going to say, well, if I follow Greg, what's my expected discounted reward? What this is saying, well, what if in just this one step I execute a different action, then I follow Greg? This is going to be the difference, right? So if it's positive, that means there's an advantage to choosing A over following Greg's policy. So with this, we can improve our policy a little bit. You could show that this is actually a better policy. We're going to call this, again, so f really is going to be the value function. We're going to call it f max, and this is the max aggregation policy. And this is basically doing what I was describing, is it's sort of looking one step in the head, one step in the future, and choosing the better action.
I'm a bit confused. Are you suggesting this? But how do you get the value function, the Q function?
Yeah, so that's yes. Yeah, right now,
Okay.
we're assuming we know the value function. Yes.
So in that case, you're done.
Yeah, you're done. Yeah. Well, then you'd have to you could do something like this max aggregation.
Okay.
Yeah.
I mean, why do you need
But maybe you could actually
to
do.
aggregate? Just take the optimal action at each step.
if you know,
Why do I need the experts?
well, the Q function is specific to a particular policy, and I'm switching policies. You might know the Q function of Greg, David, and Julia,
Oh, I see.
but I don't know the Q function of the optimal
I
policy,
see.
which might be
I see,
follow
I see.
Greg, then you right.
I see. So what you have here is the value function, Q functions for those specific.
For the oracles, and in practice, and we'll see this in a minute. We actually don't even have that. Yeah.
So here, am I allowed to take an action which is not matching any of the experts?
Yes. Yep. That's exactly it.
Isn't that a bit off? Like if I'm seeing K driving scenes, I thought our idea was to go with one of the actions.
You don't. Why? You don't have to. I mean, so there are issues that one problem that you might have if you do this, if you deviate. Okay, so if in the online setting this becomes a problem because if I take an action that is inconsistent with one of the demonstrations, it's likely that, or it's not unlikely that you'll end up in a state that was not visited by the experts or the oracles. We're calling them oracles. And so now you run into out of distribution issues. But you're allowed to pick whatever you want. We'll actually see when I talk about the two methods that I'll talk about. You can do better by doing something that's different from what all the oracles say.
So is it mathematically equivalent if I put the choice of oracle into the action space and just think of it as an action?
So in this case, then you're always going to follow what the oracle says. Yes. Yeah. So what it would be is that exactly. So my decision is now follow David now, but then follow Greg later, and then follow Julia.
So the choice of which to follow is just is an action that I take.
Yeah. But we'll show you can actually do better than that by taking in reward feedback. So that's going to give you, if you do that, you're going to get a policy that's better than any individual oracle. But you can even do better than that. Any questions?
Smoke already.
Did I? Sorry. Yep.
I mean, usually the MDP here is stochastic. I mean, even if I follow Greg, I might end in an action that I have no idea that I've never seen.
Yes.
Greg do.
Yep.
In a state, sorry, that I've never seen.
Yep,
So it's,
yep.
So
And
it's
this is a big problem with you'll get some increasing regret because of this.
Is there a way I can come up, or while choosing policies I can understand there is a policy which is better than either Greg or Julia or David, I have to start. Can I do that in this process?
Can you do what?
Can I come up or discover a more optimal policy?
Yep, exactly. So, right now there are 3 oracles. So there are 3 nominal policies. Follow Greg, follow David, follow Julia. But there are other policies that say you follow Greg now, then David later, and that's what that silly example that I had. It would be following Greg when I'm in the countryside, but then following Julia on the highway and David in the city. That is going to perform better than any of the oracles, and it will show hopefully that we can do even better than that. Okay, so again, let me skip through this. Okay, so just go to the algorithm. So this is maps. So M is multiple. APS is active policy selection, and then it's maps and state exploration. So just go through the algorithm. And so we start off with some initialized learner policies, right? So we have K+1 policies. They're the oracles, and then there's the learner. And again, we don't know V, of the oracles, we don't know Q. So we have to learn this by interacting with the oracles, by querying them. So there was, I think I had it. It's worth this great paper by Stefan Ross and Drew Bagnell from ICML 2010, and then there's some other papers by Drew's group that formulate this. It's a Dagger paper if you've heard of the Dagger method. So anyway, so we're going to do so we start off. We have V hat here. So the way I'm going to do this really is I'm going to maintain an estimate of the value function for the oracles. That's going to start off, let's say, random. And so now what I'm going to do is that I'm going to be, for some number of iterations, n or n-1, I have, this flag, basically this flag that lets me ablate, is if I'm going to do state exploration. So what I'm going to do is I'm going to start off in some state sample from the initial distribution, it was D0, and then I'm going to roll, and we call it roll in. Basically rolling in is, when we say roll in policy pi n, that's basically just execute the learner's policy. So we're going to execute the learner's policy. And then what we're going to be doing is we're going to maintain some gamma is sort of an uncertainty bound that tells us when we should switch to follow one of the oracles. So basically what the idea is that if we believe we're confident enough in the value function of an oracle, we can switch to follow that oracle. So that's what if state exploration is true. I'm going to explore by following the learner's policy. Again, when it's random, we're getting some, a little, maybe argue a little bit more exploration than we might following an oracle. And then we're going to do this until we get, again, we are sufficiently confident in the oracle's value function. Otherwise, again, this is what the baseline method did, is we're just going to sample some time over the horizon, and we're just going to roll our policy up to then, and then we'll switch to one of the oracles. And then, okay, so now what we're going to do is, so we've done this, and now it's time to switch, right? So we're going to stop listening to, we're going to stop doing what the learner's policy says, and we're going to follow one of the oracles. I'm going to call Greg and say, what would you do in this state? Okay, so that's what we're going to do.
What is this big capital smallest?
Big capital what?
Big capital T smallest. What is the symbol gamma?
Big capital T small.
So this K star ST greater than equals to.
Sorry, hold on.
In line 3 of the algorithm,
Okay, rolling policy point.
until
Gamma K star.
gamma K star is greater than gamma S. What is gamma smallest?
Gamma. Okay, that's a threshold. You pick.
Oh, it's
It's like a confidence threshold. It's a hyperparameter. Yeah. And so what we're going to do is we're going to switch. We're going to follow this policy K star, and then we're going to roll that out to collect more data. It's a fairly simple strategy. And again, this is at ICML. Last year, this was with Shuang and Takuma, Chao-Chi, and some others. Okay, so we evaluate this. Again, the previous state of the art for learning from multiple oracles was Mamba, which basically does this. They don't have state exploration or active policy selection. They basically are going to roll out, sample some time for some horizon, roll in the current learner's policy, then pick an expert to follow. Okay, so we evaluated our method map on these series of tasks from DeepMind control suite. So it's Cheetah getting this legged robot to walk. You may have seen cart pull swing up, classic task where you slide this block here, and the goal is to slide it to swing up this arm to balance it. Pendulum is another swing up task. So importantly, we'll look is that most of these are dense reward. The pendulum swing up is sparse. You only get reward when you actually swing the pendulum up, sort of like the ant navigating to the goal. So we're going to compare as baselines, as I said, Mamba, which is the previous state of the art, standard RL method, PPO, and then just look at what the best oracle is. Find the best driver and see how well could I have done if I had just followed them. So build here. So let's look. So this is the evaluation. So we're doing time versus best return. So our method is in green here, and so we see for some tasks. We'll see for the sparse reward task, for example. So the lower left. This is the pendulum swing up. So you look at PPO G8, right? So this is just doing RL. But again, it only gets reward when it happens to swing the pendulum up. So you can see it does very poor. Mamba does not do well either, but Mamba does better. So basically, so PPO does worse than the best oracle. I should say, maybe I didn't mention, where do we get the oracles? The way we get the oracles is we train a series of policies, and we take them at different checkpoints. So we get oracles that are different, behave different in different states. And with different RL methods as well, so SAC and PPO. So those are the oracles that we can pick from. Okay. So we see that basically what Mamba has learned to do is it's learned to imitate, in this example, the best performing oracle. So not bad. Other domains like Cheetah Run, where the reward is dense, the RL baseline does well, PPO GAE, but ours still learns far more efficiently, and it seems to learn a higher performant, better performant policy. There are others where cart pull swing up, which is again with a dense reward, where it looks like in this case that where PPO is competitive, if not better, with our method. But importantly, in most of these settings, not all, where you can see walk or walk. we are actually, our method is outperforming, and in the case of here, Mamba, outperforming the best Oracle. So we can actually learn a policy that's better than any individual policy, Oracle's policy.
So what is the PPO? Yeah, does this PPO-GAE algorithm have different information than you do?
Nope. It gets reward feedback. It just gets reward. So it gets different. It can't query an Oracle.
Okay.
So it's a different. It's just sort of like how would this compare to RL?
So
So that's an RL method. We're doing imitation.
intuitively, isn't it weird that the best Oracle is worse than PPO-GAE?
So it's the best Oracle, but it might be earlier on in training. So that Oracle might have been trained with PPO-GAE, but halfway through training.
Why? So then, if you pick like late enough in training some Oracle, then you're saying it'll match PPO-GAE's late performance, but you don't want to pick that.
Well, okay. So the idea is, so this is a good question. So we played around with this. How the method behaves depending on the quality of the oracles. The idea, our assumption here is that we have access to these black box oracles, and it could be that none of them are optimal. So the way that we approximate that is taking an RL method and just stopping it early and saying, well, here's a policy that learned to do something, but it didn't converge, and that's our surrogate for a person that we could query. Does that answer your question?
Yeah, in some sense, it's weird because would you have used PPO-GAE at 40 iterations or something in the wild? A person in the wild might not be optimal in all these environments, but still may be able to drive or.
Yeah. This is not to say that the PPO-GAE policy is horrible, but at least according to this metric, it's not as performant.
But then it's also weird that in the last example, Walker work,
Mhm.
the half-trained checkpoint is somehow so much better.
Well, I don't know if that's half chain. I mean, I made that half.
That's what he said.
No, that was just an example. I don't know. I think it varied for these. I'd have to look at the paper. It varied for the different domains. Yeah, I don't remember what happened with Walker Walk, but clearly, there's a large gap here. So, presumably with this Oracle is trained with PPO-GAE. Presumably with enough training steps, it's going to converge to that. 10 minutes? Is it okay? Yeah.
So could you go back to the algorithm slide? What is this? So you're doing some kind of optimism here?
Mm-hmm.
What is this sigma k? Is that?
This here?
Yeah.
This is So this is in the. I don't remember what the formulation of sigma k is. Basically, we're estimating a Gaussian distribution over the value function. That's the variance or estimator.
Okay. So I guess you're selecting policies based off of you have an estimate of the oracle.
Yep. So we have our v hat.
Yeah.
That's an estimate of the value function for the oracle, and we have some uncertainty associated with it. So the sigma expression in the discrete case.
So it's one way to think about this, you have you can think of these oracles as arms of a bandit,
Yes. Yeah. Exactly.
and then you're just trying to.
Yep.
You just want to use CPMs.
Yeah. You can think of them as exactly as arms. We'll just go through quickly. So again, just real quick, what we looked at is let's compare ourselves to Mamba. Let's see. Oops. Next slide. What do the queries of the oracle look like? So we have 3 oracles here. Red is bad. Green is mediocre. Yeah, green. I don't know why green is mediocre. Green is mediocre, and blue is good. And so we're looking at here over time is the fraction of time we query each oracle. So in the beginning, it's roughly not quite uniform, but 20% the mediocre one, maybe 60% the good one, etc. But we see with our method, it learns to draw more samples once it has a better estimate of its value function. It learns to sample or to query the good oracle more often, and the bad and mediocre oracle less often. We look at maps, and for maps, it's about the same throughout training. It's really not varying the ratio at which it's querying the different oracles. Okay. And I think I'll just skip ahead for time. Again, we have late state exploration. That was active policy selection of late state exploration. But there are still issues, right? Is that, sort of related to what Shatish was asking, is that the way the effectiveness of maps is dependent on the quality of the oracle set, right? And we saw this, right, in this card pull swing up case, where PPO actually does much better. So it is possible to do better than what our agent learned. And we also saw that in other tests where we were well behind the best oracle. So what if we could actually, use reinforcement signals from the environment to do even better than this? And I think for the sake of time, I'll skip through this. But basically, I'll show this, because the idea is fairly simple, right? So before we had our K oracles, right? K oracles I can query, the K arms I can pull. Essentially what we're going to do is we're going to take the learning agent and we're going to treat them as almost another oracle. So we have this extended oracle set where we can ask ourselves what we should do in a particular scenario. And so that's this extended oracle set, and we have an extended advantage function. The same advantage, this looks, remember, like the advantage function 4. We had F before, F max. Now it's F plus. We were running out of symbols, but again, there's a little animation here. But we add our current policy and then our estimate in practice of the value function of the current policy to this list. And so that's basically the gist. And again, for time, this is from iClear this past spring. But we get another max following, a max plus aggregation policy. Again, for the sake of time. Yes, I said, but as before, we don't know the value function, so we have this online learning setting where we have to estimate it. Again, I'm gonna skip through this. But so in theory, because we're actually getting reward feedback, we could actually do better than the policy that we would discover by combining Greg's and behavior in this state and David's in this other state and Julia's. Now I can actually use reward information to maybe say pick none of the above. And I think that was what was asked earlier. So we evaluate this in a variety of dense and sparse tasks, and we find that, so now we are evaluating again, so this method is called RPI, so the colors are not the best. We're evaluating it against maps, the previous method, and we see in some of these cases like Cheetah, dense, we significantly outperform maps. And again, there is some sensitivity for maps in this to the oracle set, to the quality of the oracles. But basically just by treating the agent, the learning agent, as another oracle, and using reward feedback, we can actually outperform what we can do by following any of it. And we can see this, right? So here's another visualization like I showed before. What we're showing again is training time here, the frequency with which we queried an oracle. Now there are 4 oracles, one of them being the learner. I don't know what the ranking of blue, orange, and green was, but we see what's happening over time is in the beginning it's not at all, the value function of the learner is very low. So it's not querying the learner, it's going to query the oracles. But over time, as the learner becomes more proficient, it starts querying the oracle more often. The learner more often, and the oracles less often. And near the end, roughly 80% of the time, it's querying itself. It's now learned a policy that's better than any of the oracles. Okay, so I think maybe 5 minutes. So one issue with this work is that learning from demonstrations, I need actions, right? I need to be either Tesla, where I can crowdsource, or maybe physical intelligence, however they're doing it, collecting a lot of labeled demonstrations. When I say labeled, I mean we have the action is supervised. But those are difficult to collect. I don't know what physical intelligence paid. Some of you have collected data with the robot in the lab. It's slow. It's non-intuitive. It's not going to scale. That's right. There's a clear scarcity compared to other domains of embodied data, action-labeled data, or Oracle access. And so that limits scalability or limits practicality. But on the other hand, there's internet scale human demonstration videos out there. It's great YouTube. But they don't provide actions. So what can we do? And so this is one, you may be familiar with it, Ego 4D, around almost just shy of 4,000 hours, almost 1,000 different participants, 9 different countries, performing a variety of tasks using an egocentric camera. And just showing the magnitude. So, it's many hours. But of course, they don't have labels, right? There are no actions. So, can we do something with this and make it usable for a robot? And this is actually just a CVPR submission about maybe 12 hours ago. So we have this method, progressor. And the idea is fairly simple. We're gonna take some network, and this network, we would like this, we're gonna give this we have some task, right? And then this is a goal condition task. So the task, for us, the goal is gonna be the goal image. And we have the initial image. And what we want this network to do is to, given the initial image and the goal image, tell me how far along we are. Are we 25%, making 25% progress? Are we almost at the end, etc.? So it's trained to predict progress. And we can do this in a self-supervised manner. We scrape videos from not Ego4D because it's too big, but we do Epic Kitchen. And we can train this in a self-supervised manner to predict progress on these tasks. So these human videos. And the idea now is that we can use this prediction as a signal for an RL agent. So if the progress prediction is low, I want to penalize the robot. If the predicted progress is high, I want to give the robot more reward. So you could sort of think of this ant navigating. It's not just one when you get to the goal. It's you're giving it reward based upon the inverse distance to the goal. So that's the idea. Now there are some challenges. One is that, well, this distribution shift. The videos that we have are human videos. Humans generally do things pretty well. Early on in training, the robot policy is going to be doing things that are random. So the observations you're going to get are going to be very much out of distribution compared to, there's going to be the clear distribution shift compared to what you saw in these demonstrations. So our reward model is going to predict, random values. And that's not useful because that might falsely incentivize undesired behavior. So that is progressor, and again, I'll try to go through this very quickly, but there are basically 3 parts to this. There's this offline pre-training where we have, again, we're going to estimate not just a scalar progress, but a distribution over how far along you are, 0 to 100%, right? So we take our initial image, the goal image, and where the current image along this video, right? And we do this we train this on human video, or in some of the results robot videos. And the goal is just to match some target distribution, how far along the video. Okay. Now, as I said before, there's going to be this scenario is when I'm deploying this on the robot, I'm going to get things that are out of distribution. So we have this adversarial method which we call pushback, where we basically take instances early on in demonstrations from the robot, and we encourage the model to push those back to estimate lower progress than is actually being made. And that's essentially it. Now what we can do is we can use this as a reward signal. So we've done this. We looked at a series of again, robot manipulation, opening a door, opening a drawer, etc. And we compare this to state-of-the-art baseline, so VIP, R3M, rate to reward is another one, Gale, time contrasted networks if you're familiar with that. And again, this is a lot to digest, but higher is better. And so we see in some tasks, our method is significantly outperforming all the baselines. And to be clear, this is in simulation, and the reward prediction model is not trained on Epic Kitchens. It's trained on videos of the robot performing tasks. So videos of that robot performing these tasks, or a set of tasks, really. But not the tasks that we're actually performing. So these very hard tasks like, door opening. Closing a drawer is relatively easy. Opening a drawer is very difficult. So now what we're showing is success rate. And it's not, there are some issues. So if you look at actually this reach task is really easy. So what happens in reach, if you actually look at it, you might wonder, why is the success rate going down? With more training, it's actually getting worse. Well, the problem with reach, or actually the issue with reach is that it's a pretty easy task. The goal is to go from here to here. But again, we have this pushback, and we're telling the model that, well, the actions of the policy early in training are not very good. So we're telling our reward model that these actions here are not good. Try to, you should be predicting poorer progress. And so in this case, for tasks that are easy, when the robot is actually doing something, or the policy is doing something reasonable early on, it gets penalized, and so the success rate goes down. But compare this to all these other methods, how quickly we converge to, like it's not, it's 50 some % success. Okay, so just very quickly. We also did this in the real world. So this, we took our model as a ResNet backbone, and we trained it on Epic Kitchen's video, sort of like Eagle 4D, but much smaller. And we do this a little bit, again, it's not RL. 1 minute, okay, I'm almost done. So we do this in a slightly different way. So what we do is we treat this sort of like a behavioral cloning or imitation learning. We collect, for each task, opening a drawer, closing a drawer, 20 demonstrations. 10 of them utterly fail, 10 of them succeed. But the ones that succeed they're different, they're noisy. And what we want to do is, if we train this on imitation learning, it's a behavioral cloning loss. What it's going to do is it's going to regress to the mean, and it's going to pick something in between the two, and that's what we see. And for most tasks, it doesn't do well. So what we're going to do is we're going to use our reward model to see if we can differentiate between good demonstrations and bad demonstrations. And that's basically it. Now, again, this is just predicting progress. It's all in the, well, you can't get the paper because it's not out yet, but soon it will be. So let's look at the VIP baseline. So this is a paper from, a year ago or so out of UT Austin and UPenn. So the goal is to simply pick up this cup, put it in the bin. And the goal just is an image of the cup in the bin. And VIP just fails. And we look at our method progressor. Maybe we look at it, maybe we don't. There we go. It's not going to be doing my dishes or loading my dishes anytime soon. But it's able to perform the task. And we compare this to R3M, other baselines as well. Much harder task is opening this drawer. In this case, even collecting demonstrations of this task is difficult. And surprisingly so this is the baseline R3M. So basically it regresses to this mean. That was the failure mode for the ones. They almost got there and they pulled back, but they weren't holding that. We look at ours. Should speed these up. But you can guess, right? It's going to grab the drawer and pull it open. And so we see this, the success rate for ours, these 4 tasks, is drawer close, as I said, is easy, so most methods. ACT here is just a behavioral cloning baseline. So for pick and place cup, it fails all the time. Push block, it fails. Close drawer, open drawer, it fails. Okay, I'm done. This is the last slide. So we want to see, well, why is this happening? Let's take our demonstrations and let's see how well our method progressor is able to tell good demonstrations from bad demonstrations. And that's what we're looking at here. So we're coloring, this is averaged over a set of demonstrations. The correct demonstrations, the ones that perform the task, are in blue. The ones that failed are in yellow or orange, whatever they call it, orange. And what you get, the way we're learning from these is we're going to weight these. Basically, it's how much we're going to penalize the loss for not matching the demonstration. So if you look at our method, it clearly is distinguishing between, just from the reward trained on Epic Kitchen, between good demonstrations and bad demonstrations. You look at R3M, and it's really not telling. Maybe there's some signal here after 200 steps. VIP, similarly, it's not able to tell them apart. So that it gets this averaging behavior. Anyway, so that's that. That's it. So the 2 papers, ICML and iClear, are on the website and archive. Hopefully CVPR will be on archive soon. So that's it.
Questions? Yeah.
I had a question about those oracles.
Mhm.
So could you also accommodate the oracles themselves learning because you accommodate your own policy?
Yeah, I guess you could do this. So with the second method that I talked about, you can imagine the oracles themselves adapting.
So you could use all the things you compare against themselves as oracles and then learn your policy. I
see. So you're talking about the baselines, like the Mamba? Yeah, you could do something like that. I mean, it might be a little bit tricky because you're estimating this value function, but it's a moving target because the policies are changing. So that's challenging. But in theory, you could do that. I mean, you're doing that with the learner's policy. So.
So in this last experiment, what's few shot? So are there both the good and bad demonstrations there? Like very few examples of each one?
Oh yeah, so there are 20 total. Yeah, we have 20 demonstrations per task, 10 that fail, 10 that succeed. So Tianzhong, I think, did them all. So he opens the drawer 10 times, and 10 times he doesn't open the drawer.
Okay, so intentionally, or is it?
Yeah. We wanted to get a mix of good and bad behaviors. It could be like I open it and he opens it and I wouldn't be able to do it. He would be able to do it, so I would be the failures. No? Does that answer your question?
I have a question about pre-training. Remember a paper from Abhinav Gupta and Deepak Pathak from last year, which showed that for most of the robotics tasks, pre-training on Epic Kitchen is a bad idea, where they show pre-training on ImageNet is much better than pre-training on.
Okay, I'm not familiar with that.
So I was wondering if you write other pre-training strategy and see if it.
I mean, how do we treat for the Epic Kitchen model? Was it pre-trained on anything else, or was it just initial from scratch? Wow. Yeah, clearly there's this distribution shift, right? These are videos of humans.
That's the conclusion from the paper. The Epic Kitchen is not diverse enough, so it usually does not generalize us to most of the robotics tasks. And ImageNet is.
So this is a video. So on the top we have the frames from this video, and we have the plot prediction. So this is trained on Epic Kitchen and evaluated on a robot task.
Right.
So very odd distribution. Again, it's not seeing much of the robot, but we're getting, then again, this is the goal image, so the cup in the box. And we're getting reasonable predictions of progress despite this disparity. But again, we've done this with 4 or maybe 5 different tasks, so you've not looked at it exhaustively.